Hello my schoolers, this is my school YouTube channel and my name is Frank. In today's video, we shall be dealing with structure of the nucleus part 2. Now remember that in our previous video, we dealt with the part 1 where we covered the models of the atom, atomic structure and property, isotopes and other related topics. Okay, so in today's video, that is the part 2 of the structure of the nucleus. We are basically going to focus on radioactivities and nuclear reaction and other topics. So relax, do not go anywhere, I'll be right back. You are welcome back to my school YouTube channel. Like I said, in today's video, we are going to be dealing with structure of the nucleus part 2. So before we begin with our lesson, let's quickly run through the objective of today's video's lesson. So objective number 1, identify the radiations from radioactive substances using their characteristics to solve simple problems involving half-life of radioactive substances. 3, state some uses of radioactive substances. 4, determine the products of a radioactive decay. So let's move to the next slide to begin with our lesson. So in the first slide, basically we are going to be looking at the meaning of radioactivity, then radioactive elements, and then types of radiation. Okay, so let's begin with the meaning or the definition of radioactivity. So radioactivity is the spontaneous decay or disintegration of unstable nuclei of the atom of an element by the emission of alpha particles, beta particles, and gamma radiations with the production of energy. Okay, and this energy is in the form of heat. Okay, so the phenomenon of radioactivity was first discovered by Henry Becquerel. Okay, so he was the first to do some work on radioactive substances. Okay, so what do we mean by radioactive elements? So radioactive elements are those elements that spontaneously emit radiation from their nucleus. And examples of such elements are radium, thorium, radon, uranium, polonium, etc. Okay, so we have many of them. Now let's move on to talk about types of radiation. Okay, so in an experiment where a small sample of radium was placed at the bottom of a small hole drilled in a block of lead, the radiation emitted from the sample emerged from the hole in a narrow tube. Okay, and the rays were subjected to a strong magnetic field, okay, in bracket band magnet, placed at the sides of the beam. So this is just the experiment, okay, that enabled the scientists who worked on radiation to discover the different types of radiation. Let's move to the next slide to continue. So a photographic plate placed in front of the beam showed that the path of some rays were bent to the right, some to the left, and some went straight on, unbent. The same effect is observed when electrically charged plates are placed at the sides of the beam of the magnetic field. So this is the diagram representing that experiment. So this is the lead block, okay, with the little hole in the middle, right? And this is the radioactive material that was placed inside the hole. And these are the different radiations that were given out from the radioactive sample or radioactive materials. Okay, and these are the radiation. You see some bending to the left, some bending to the right, and there's one just pointing straight. So the same thing happened, okay, when an electric field was employed instead of magnetic field. Okay, so let's move to the next slide. So the radiation that was bent towards the south pole or the negative electric plates shows that it consists of positively charged particles. Okay, and these positively charged particles were called alpha particles, and alpha particles is represented with this symbol. Okay, so this is the alpha symbol, while the radiation that was bent towards the north pole or the positive electric plate shows that it consists of negatively charged particles. These negatively charged particles were called beta particles. Okay, so this is the symbol of the beta. Okay, so those ones were called beta particle, while the third radiation, okay, was neither deflected by the electric or the magnetic field. This shows that it carries no charge. They were actually an electromagnetic radiation and they are called gamma rays. Okay, so from here you can actually see that unlike charges attract, okay, and the like charges repel, right? So the particle, okay, that was attracted or that bent, okay, towards the south pole or the negative electric plate shows that it consists of positively charged particles, and those particles were called the alpha particles. While the one that was bent towards the north pole or the positive electric plate shows that it consists of negatively charged particles, and those negatively charged particles were called beta particle. Then there's another one that was neither deflected by the electric nor the magnetic field, and that one, it was discovered that it carries no charge. That is the reason why it was not deflected at all. Okay, and it was discovered that they were actually electromagnetic radiation, and those ones are called gamma rays. Okay, now let's look at the properties of these emitted particles, right? So here we have radiation, then we have the different types of radiation, that is the alpha particle, the beta particle, and the gamma rays. Okay, so we are going to be looking at their nature first of all. So for the alpha particles, by nature they are helium nuclei, 42He. Now remember, the 4 there represent mass number of helium, while the 2 there represent the atomic number of helium. Okay, so by nature alpha particles are helium nuclei. Okay, while by nature beta particles are high energy electrons. Okay, while by nature gamma rays are electromagnetic waves of short wavelength. Remember, lambda represent wavelength. Okay, it's the symbol for wavelength. So gamma rays by nature are electromagnetic waves of short wavelength. Now let's move to the next slide to see other properties. Okay, so the velocity of alpha particle ranges between 0.15 to 0.25 times 10 raised to power 8 meter per second. Okay, while the velocity of beta particle travel at approximately the speed of light. Okay, while that of gamma ray has the same speed as the speed of light, that is 3.0 times 10 raised to power 8 meter per second. Now let's talk about their charges. Okay, so for alpha particle the charge is plus 2e, right? Here the 2e there means that helium particle has 2 protons. Okay, and that's equivalent to 3.2 times 10 raised to power minus 19 coulombs, while for beta particle minus e, okay, that is equivalent to minus 1.6 times 10 raised to power minus 19 coulomb. While for gamma rays, okay, they are electrically neutral, meaning that they carry no charge, they have no charge. Now let's talk about their masses. So for alpha particle, the mass of alpha particle is 6.65 times 10 raised to power minus 27 kg, and that is relatively massive, while that of beta particle is 9.1 times 10 raised to power minus 31 kg and is considered relatively light, while the mass of gamma rays is negligible. Okay, so it's something that can be ignored because it's very, very small. Okay, now let's talk about the effect of magnetic field. Okay, under magnetic field, the alpha particle shows slight deflection towards the south pole, while for beta particle it shows strong deflection towards the north pole, while for that of gamma rays, magnetic field has no effect on the gamma rays. Okay, now let's talk about ionizing power, right? So for alpha particle, okay, ionizing power, or you undergo heavy ionization, okay, or it brings about heavy ionization, while for beta particles it is that of medium ionization, while for gamma rays it's little ionization. Okay, so of all the 3 particles, probably if you are asked which of them have the highest ionizing power, so in this case your answer should be alpha particle, and if you are asked which of them has the least, then in this case your answer should be gamma rays. Okay, now let's talk about penetrating power. Okay, so for alpha particle, little, it can be stopped by paper. Okay, it's little, the penetrating power of alpha particle is little, it can be stopped by paper. Okay, while for gamma particles, medium, several millimeters of aluminium, okay, can stop the beta particles, okay, the movement of the beta particles, while for gamma rays high several centimeters of lead. Okay, so in terms of penetrating power, if you are asked which of the particles have the highest penetrating power, in this case your answer should be gamma rays. Okay, because to stop gamma rays you need several centimeters of lead. Okay, while which of them has the least, then in this case your answer should be alpha particle, because it can be stopped by papers. Okay, so these are the characteristics, or these are the properties of the different types of emitted radiation. So let's move to the next slide to continue with our lesson. So on the other slide here, we are going to be talking about the types of decay. Okay, so based on the types of radiation, we actually have 3 types of decay. Okay, so we are going to be discussing them one after the other. So the first type of decay we have is called the alpha decay. Okay, so alpha decay brings about the emission of alpha particle. Okay, so when a nucleus emits an alpha particle, its neutron number n and proton number z each decreases by 2, and the nucleon number A decreases by 4. So when we say nucleon number, basically we are referring to mass number. Okay, so the nucleon number decreases by 4, but the neutron number and the proton number, which is the same thing as the atomic number, decreases by 2. So generally an alpha particle is denoted by this nuclide that is on the screen now. So AZS. Now remember that A stands for the nucleon number, okay, and ZS stands for proton number, right? So during alpha decay, okay, what happened is that the mass number, okay, or the nucleon number decreases by 4, while the proton number, okay, and the neutron number decreases by 2, okay, accompanied with emission of energy in the form of heat, right? So Q is the energy produced in the process, and a good example is that of radium. So radium here undergo decay. So radium undergo decay by emitting an alpha particle. So by emitting an alpha particle, it produces random, that is random 222 then 86, okay, with the emission of energy, as you can see on the screen. Now the second type of decay that we have is the beta decay. So the beta decay usually leads to the emission of beta particles. Okay, so in beta decay, N, which represents neutron number, decreases by 1, and Z increases by 1. So remember, Z there stands for atomic number. Okay, so the atomic number increases by 1, but the neutron number decreases by 1. Therefore the nucleon number A does not change in the case of beta decay. So generally a beta decay is denoted by this equation. Okay, so remember AZS here represents a nuclide, right? So during this decay, atomic number increases by 1, right? The neutron number decreases by 1, but the mass number still remains the same, or the nucleon number still remains the same, with an emission of energy. So let's move to the next slide to see the other type of decay. But before then, let's see an example. So this is beryllium 11, okay, undergoing decay. So beryllium 11 undergoing decay still produces beryllium 11. Okay, but you can see here that here the atomic number has increased, or the proton number has increased by 1, okay, with an emission of a beta particle accompanied by the release of energy. Okay, then we also have another one under beta decay, which is beta particle emission, positron. Okay, so A is unchanged, but Z decreases by 1. So remember that the A there represents mass number, while Z represents atomic number. Okay, so in this case it's positron, in the sense that the electron here emitted is positive. Okay, so here what happens here is that the atomic number decreases by 1, while the mass number remains unchanged. So in this case we call this positron. Okay, because the electron here is positive, carrying a positive sign there. Okay, while the third type of decay is called the gamma decay. So the gamma decay leads to the emission of gamma radiations. Okay, so in gamma decay, the elements undergoing gamma decay does not change in nucleus. It only goes from an excited state to a lower state, that is, moves from an unstable state to a stable or to a more stable state. So the emission takes place from an excited nucleus with no change in nucleon or proton number. So everything remains the same. Mass number remains the same. Atomic number remains the same. Nothing changes at all. So generally, a gamma decay is denoted by the equation you are seeing on the board. So if you check very well, nothing changed. So this is gamma, okay? This is gamma radiation or gamma ray. So the atomic number remains the same and the mass number too still remains the same, but it's usually accompanied with a release of energy. And a good example is cobalt-60, okay? So cobalt-60 here undergoes gamma decay, so nothing changed. Okay, so the cobalt-60 still remains. So what actually happens here is that this cobalt-60 you have here on the reactant side is the unstable cobalt, but here the one you have in the product side is the stable cobalt. Okay, so this is also accompanied with the release of energy. Let's move to the next slide. So on the next slide there, we are going to be discussing about the law of radioactive decay. Okay, so the law states that the number of radioactive nuclei decaying per unit time is directly proportional to the number of nuclei n present at that instant. That is, the n over the t is directly proportional to n. Okay, now of course remember this is just a relationship, so we cannot really do anything with this. So therefore the n over the t is equals to minus lambda, okay, n, right, minus lambda n, and we call this equation 1. Okay, so if we decide to switch the positions of the t and the n, then we'll be having the n all over n is equals to minus lambda dt, and we call this equation 2. Okay, now the negative sign here, okay, shows that the radioactive nuclei decreases with time. That is just what that negative sign there represents. Okay, so lambda is the constant of proportionality called the radioactive decay constant. Okay, so if n naught is the number of radioactive atom or nuclei present at a time t is equals to 0, and n is the number at the end of a time y, then by integration of both sides of equation 2, okay, which is this, we have that n is equals to n naught, then exponential minus lambda t, and we call this equation 3. So we have to take note of this equation. Now let's move to the next slide. So basically here, what we are trying to achieve is just to make the lambda the subject of formula here. Okay, so now let's define some of all those terms that we got from equation 3. So n is equals to number of undecayed atoms left, while n naught is equals to initial number of atoms or nuclei present, while t is equals to instant of time. Okay, so since the rate of disintegration or activity A is proportional to the number n of disintegrating atoms, and n is equals to n naught exponential minus lambda t, then A is also equals to A naught exponential minus lambda t, where A naught is the initial rate of disintegration or activity of the atom. So now let's talk about the decay constant proper. Okay, so decay constant is defined as the instantaneous rate of decay per unit atom of a substance, or is the fraction per second of the decaying atom, or you can as well define it as the probability of an atom decaying in the next second. Okay, so from equation 1, remember our equation 1, it was dn dt is equals to minus lambda t. Okay, that is our equation 1. So minus lambda n, sorry, so that was our equation 1. So from there we can decide to make that lambda the subject of formula. Okay, by simply, okay, let me even write it down and show us how this equation came about. So this was our equation 1, dn over dt, right, was equals to minus lambda n. Right, so basically here we want to make this the subject of formula. So to do that, we have to divide both sides by minus n, right? So to divide both sides by minus n is the same thing as saying multiplying both sides by minus 1 over n. Okay, so if we multiply both sides by minus 1 over n, we'll be having here times minus 1 over n, And on this side, we'll also be having minus 1 over n. So minus, we cancel out minus, n, we cancel out n. So that at the end of the day, we'll be having our decay constant to be equals to minus 1 over n dn over dt. Okay, so basically that's how we obtain this equation from equation 1 above. Now let's move to the next slide. So remember that decay constant is also equals to number of disintegrating atoms per second all over number of atoms in the source at that time. Now let's talk about half-life and how that decay constant is related to half-life. Okay, so the half-life of a radioactive element is the time taken for half of the atoms initially present in the element to decay. Okay, so for a half-life, n is equals to n naught all over 2. Okay, so putting this in equation 3. Now remember that our equation 3 was n is equals to n naught exponential minus decay constant t. So this was our equation 3, right? So putting this, which is putting n equals to n naught over 2 in equation 3, okay, and t to be equals to half-life, okay, because t then 1 over 2 is actually how we write half-life. So if we put this into this equation, we will have n naught over 2 is equals to n naught e then minus exponential t. So that if we decide to divide both sides, okay, by n naught, we'll be having 1 over 2 is equals to exponential minus decay constant, okay, then times half-life. Right? Now, taking the natural logarithm, that is in or log e, of both sides, we have that in 1 over 2 is equals to minus decay constant times half-life. Okay, so just take note of that. Now, this is how we obtain this 1 over 2. So it's very easy. Now, since we have n naught over 2 here, and we also have n naught here, and we want to eliminate the n naught. So basically, what we do here is actually to multiply both sides by 1 over n naught. Okay, so if I multiply here by 1 over n naught and multiply this side by 1 over n naught will cancel out n naught on this side because it's now a fraction. So we're actually having this n naught times 1 over n naught. So these two will cancel out. So on this side it will cancel out. While on this side we have n naught all over 2 times 1 over n naught. So in the same way it will still cancel out. So that's how we arrive at this 1 over 2 is equals to exponential minus decay constant times half-life. Okay, so taking the natural logarithm, that is in or log e of both sides, we have that in 1 over 2 is equals to minus, right? So the essence of that is because we want to eliminate this exponential. So that is the reason for taking the natural logarithm of both sides. So if we do that, we'll be having in 1 over 2 is equals to minus decay constant times half-life. Now let's move to the next slide. So, but remember that in 1 over 2 is the same as saying in 1 minus in 2. Okay, so in 1 is equals to 0, while in 2 is equals to 0.693. Right? So 0 minus 0.693 is equals to minus 0.693. Okay? So therefore, in 1 over 2 is equals to minus decay constant times half-life. And this becomes, now since in 1 over 2 is equals to minus 0.693, okay, so minus 0.693 now replaces in 1 over 2. So that we'll be having minus 0.693 to be equals to minus decay constant times half-life. So minus we cancel out minus. So that 0.693 is equals to decay constant times half-life. So here we want to make half-life the subject of formula. So to do that, we simply divide both sides by decay constant. So that half-life is equals to 0.693 all over decay constant. Okay, so with this formula you can either calculate for decay constant or you can calculate for half-life. If, for example, the half-life is given to you, you can calculate for decay constant, or if decay constant is given to you, you can calculate for the half-life by just using this formula. Okay, so a graph of n against t called decay curve is as shown. Okay, is as shown. So this is the graph called decay curve, right? And it's a graph of n, okay, against time. So let's move to the next slide. Now let's talk about the types of radioactivity. So basically there are two types of radioactivity, namely natural radioactivity and artificial radioactivity. So when we say natural radioactivity, we are referring to that type of radioactivity that involves the spontaneous disintegration of an unstable nuclide by the emission of alpha particle or beta particle or gamma radiation, or a combination of any two or all three with energy released. Okay, so for natural radioactivity to occur, this is very important, the proton number, okay, Z, must be greater than or equal to 82. Okay, the proton number must be greater than or equal to 82. So the proton number there represents atomic number, okay, and it must be greater than 82 for natural radioactivity to occur. So let's see some examples. So example 1 is radium-226 decays to radium-222 by emitting an alpha particle. Okay, so this is just the equation for the reaction. Okay, so this is radium-222 emitting an alpha particle to produce radium-222, okay, plus the release of energy. Now let's move to the next slide to see more examples. Now example 2, radium-222 decays to polonium-218 by emitting one alpha particle also. So here we have our radium-222. Okay, so radium-222 undergoes natural disintegration or spontaneous disintegration, emitting an alpha particle to produce a new element or a different element, polonium-218, accompanied with the release of energy. Then we also have another example, which is uranium-238 decays to thorium-230 by emitting two alpha particles and two beta particles. Now take note that this reaction does not occur in just one step, okay? It occurs in sequence of steps, okay? But here the final result is just combined, okay, to produce this equation. So this is uranium-238, okay, undergoing decay to produce thorium-230 by the emission of two alpha particles and two beta particles, okay, accompanied with the release of energy, right? Now take note of these points I'm going to make now. So to balance a nuclear equation, we ensure that the sum of the numbers Z or subscripts must be equal on both sides of the equation, and the sum of the nucleon number A or superscript must be equal on both sides of the equation. That's just how you balance nuclear reaction. Now let's look at this, if this is actually balanced. So if you check very well here, okay, so the nucleon number here on the reactant side is 238. While the nucleon number here, to obtain the nucleon number on the product side, you have to add all the nucleon numbers here. For example, you add that of the alpha particle, you also add that of the beta particle, okay, plus that of the thorium to obtain the same nucleon number as that of the product. So in this case, the mass number here for the helium is actually 8, because this 2 is affecting every numbers in front of it. So 2 times 4, that will be 8. Then 2 times 0, that will be 0. So 8 plus 0 is 0, right? Now remember that of thorium, that is, the nuclear number of thorium is 230. So 8 plus 230, that will be equals to 238, and which is the same thing as that of uranium-238. That is how we balance nuclear equation, just making sure that the nuclear number on the product side is equal to the nuclear number on the reactant side, okay, and the atomic number on the reactant side is equal to the atomic number on the product side. Okay, now let's talk about the other type of radioactivity, which is known as artificial radioactivity. So all these ones, artificial radioactivity doesn't occur naturally, okay, it must be instigated, okay, before it occurs. So artificial radioactivity is a phenomenon in which an ordinary material, not normally radioactive, is made radioactive by bombarding it with radioactive particles. Okay, that is artificial. So artificial is it's man-made, it's instigated, okay, by bombarding it with radioactive particles. So let's move to the next slide to see an example. Now, so let's see an example. One of them is non-radioactive element, okay, non-radioactive aluminium. So this non-radioactive aluminium is not a radioactive element, okay, it's just normal aluminium. So, but this non-radioactive aluminium is bombarded with an alpha particle to produce a non-stable phosphorus, which disintegrates spontaneously into stable silicon. Okay, so this is the alpha particle and this is the non-radioactive element. Okay, so when alpha particle is used to bombard this non-radioactive aluminium, okay, an unstable phosphorus 30 was produced, okay, which again was bombarded with neutron, okay, and that produced stable silicon, okay, with the release of energy. So here we have helium, aluminium, phosphorus, neutron, silicon, then we have positron, then we have neutron again, and the energy that was released. So second example is nitrogen being bombarded with an alpha particle to produce an unstable isotope of fluorine, which disintegrates into an oxygen nucleus and a proton. So this is the alpha particle that was used to bombard the nitrogen, and this produces fluorine 18, right? So this fluorine 18 disintegrates to produce oxygen, okay, and proton, or we can say ordinary hydrogen, then plus energy. So we have helium, nitrogen, fluorine, oxygen, proton, okay, or you can say ordinary hydrogen, then plus energy that was released. So the neutron, the proton, and the alpha particle have been found to be very effective bombarding projectiles for disintegrating the nuclei of elements. Now let's see some example based on this in the next slide. So here we have nitrogen, magnesium, sodium, hydrogen. Okay, so in this reaction, magnesium nuclei changed into sodium nuclei. This is called transmutation of atoms, right? So we'll have another example again: proton, beryllium, then lithium and alpha particle, then another one, alpha particle, beryllium, carbon, neutron. Okay, they are all examples of artificial radioactivity. Okay, so here are some worked examples for us to go through just to drive home what we have seen so far. So example 1, a nuclear reaction is represented by the equation below. So here we have aluminium 27, okay, plus neutron, and that produces sodium 24 plus S plus energy. So the product denoted by S is, so basically they are asking us to find the product, what this S represents, right? So basically it's just for us to balance this equation, right? So we just make sure that the nuclear number on the reactant side is equal to the nuclear number on the product side, okay? And the atomic number or the proton number on the reactant side is equal to the atomic number or proton number on the product side. Now forgive me that I'm using the word product and reactant, okay? This is actually a nuclear reaction. Okay, so if you check very well, if we should add this together, we'll be having 27 plus 1. That gives us the nuclear number on the reactant side, right? Then if we add 13 and 0, that also gives us 13. But if you look at here, we have 24, right? And here we have 28. So that means we need extra 4. So on the nuclear side here, on the S side here, we need 4 here, okay? So that the nuclear number on the reactant side is equal to the nuclear number on the product side. Now here we have 13 and 0, which is 13, but on this side we only have 11. So that means we need extra 2 to make it 13. So here will be 2. Now if you see this, whenever I see this nuclide, okay, 4, 2x, just know that this actually represents a helium nuclei or an alpha particle, okay? So the product donated by S is an alpha particle, or you can say a helium nuclei, Okay, now let's move to the next slide to answer example 2. So for example 2, we are given this equation. Okay, so 2311A plus 21B is equals to PQC plus proton, then PQC then gives you RXE plus beta. So a nucleus C formed artificially from A and B is radioactive and quickly disintegrates to another nucleus E as indicated in the equations above. Determine the values of P, Q, R, and X. Okay, so the idea still remains the same. Now remember that your proton, okay, you must take note of this. Your proton is 1H1. Okay, so that means we already have 1 here, okay, for proton, right? So if we add the nucleus number for these two elements together, so that will be equals to 25. Okay, so on the reactant side, we already have the nuclear number to be equals to 25, right? Then let's do the same thing for the atomic number. So if we add 11 and 1, that is already 12. So we have 12 here, right? So for the product side, so since we already have 1 here, that means we need extra 11, okay? While on the other side, we need 24, right? Okay, so now our C is 24 and 11. So in this question, we actually asked to determine the value of P, Q, R, and S, meaning that we've already determined the value of P and Q. Okay, so the value of P, let's just write it out. The value of P is equals to 24, okay, while the value of Q is equals to 11 based on this. Okay, now let's move on to provide answer for E. So we already know this now. So here is 24 and here is 11. And here we have arrow and here we have X. Now for beta particle, remember that beta particle is 0, okay, minus 1 E. That is beta particle, right? So if we are subtracting 1, that means here we are going to be having 12, okay? Here we are going, for E, we are going to be having 12 here, while here still remains 24, okay? While here still remains 24, because 24 plus 0 still remains 24. And on this place, our P is 24. Now our Q is actually 11, okay? But here we are having minus. So 12 minus 1, that will also be 11, okay? So the value of arrow, okay, is equals to 24, while the value of S is equals to 12. Okay, so as you can see, the equations are balanced. Okay, now let's answer question 3. A radioactive substance has a half-life of 3 days. If a mass of 1.55 grams of this substance is left after decaying for 15 days, determine the original value of the mass. Okay, so in order to answer this question, we will have to move over to the board. So let's provide answer to this question on the board. So let's look at the question basically. Now, one thing you must note is that we are supposed to use N is equals to N naught exponential minus decay constant times half-life. Now, if we are to use this, it's going to take us a lot of time. But just take note that this equation actually implies this. Okay, implies N is equals to N naught, then bracket 1 over 2, then bracket N raised to power N. Okay, so this equation implies this. Okay, so if we are to work on this, okay, basically we are going to be having 1 over 2. Okay, now remember that N there means number of half-lives. Okay, and number of half-life N is equals to T all over half-life. So take note of this. So in this question, we are asked to determine the original value of the mass. So the original value of the mass has to do with N naught, right? So we don't know, but we know N to be equals to 1.55 grams. So we'll just take note of that. So in this question, half-life T 1 over 2 is given to us to be 3 days. Okay? While the small letter T is given to us to be equals to 15 days. So from here, we can actually calculate for the number of half-lives. So the number of half-life in this case, which is that small n, because we are using this formula, not this. So if we are to use this, it's going to take us, we will have to need calculator. We need calculator to do that. But what of if maybe, let's say you are in JAMB exam now where you don't use calculator? So what do? So it's better you just get used to this formula instead of using this. But this implies this. So these two are also correct. So if you have your calculator, you can make use of this formula, though the process will be a little bit longer, okay, because you have to calculate for decay constant first, then you substitute, then multiply by the half-life, which is given to you in the question, then before you now look for exponential, whatever the value you obtain from here, okay, you obtain from here, look for the exponential of it, then before you now divide. So it's going to take a lot more time. So it's better you make use of this equation, okay? So here we are actually looking for N naught because that represents the original value of the mass, right? So here we know T to be equals to 15, and half-life to be equals to 3. So you'll be having 15 all over 3, and that will be equals to 5. So N is equals to 5. Now we can now substitute all these values into this equation, right? So we know N to be equals to 1.55, and that is equals to N naught. We don't know what we are looking for. Then bracket 1 over 2 raised to power 5. From our calculation here, N is equals to 5. Now, 1 raised to power 5 is still 1. But 2 raised to power 5 is 32, right? 2 times 2, that is 4, times 2, that is 8, times 2, that is 16, okay, times another 2, that is 32. So 1.55 is equals to N naught, then times 1 over 32. And this is the same thing as say N naught all over 32. So that 1.55 is equals to N naught all over 32. Now, since we are calculating for N naught, which is the original value of the mass, right, we just cross multiply. So if we cross multiply, N naught will be equals to 1.55 times 32, okay, and this will be equals to 49.6 grams, okay. So the original value of the mass is equals to 49.6 grams, okay. So let's return back to the screen to answer the remaining question, okay, and that should be example 4, okay. So the equation for radioactive decay is N is equals to N naught exponential minus decay constant times time, okay. We are being asked in this question that what does N naught represent, and that we should state the unit of decay constant, okay. So N naught here represents the initial number of atoms, okay, or nuclei present in the given sample or present in the given material. N naught here represents the initial, or you can say the original number of atoms or nuclei, okay, present in the given sample, okay. While we are asked to state the unit of decay constant. Now remember here, lambda here represents decay constant as far as radioactivity is concerned or nuclear reaction is concerned, okay. So the unit of decay constant is per second, and it's written like this, x raised to power minus 1, okay. So the unit, the SI unit of decay constant is per second. Now let's answer the III, okay. A sample of radioactive material has a half-life of 20 hours. What proportion of the original radioactive nuclei will remain after 80 hours? What proportion, okay, of the original radioactive nuclei will remain after 20 hours? So when they're talking about proportion, basically they're talking about fraction, okay, or those are two words that are used interchangeably in mathematics. Okay, let's move over to the board to provide answer to this question. So we are going to be using N is equals to N naught bracket of 1 over 2 raised to power N. Now remember I told you that N is equals to N naught exponential minus alpha, then T1 over 2 implies this equation. Okay, so here in this question we're actually looking for N all over N naught. Okay, so if we do that by simply dividing both sides by N naught, this will be equals to 1 over 2 raised to power N. So remember that N, which is small letter n, is equals to T all over half-life, right? So in the case of this question, half-life is equals to 20 and that small letter t is equals to 80, right? So 0 cancels 0, and 8 divided by 2, that will be equals to 4, right? So our n is equals to 4. So in place of small letter n here, we just replace it by 4. So that will be having n all over n naught, which is the proportion of the original radioactive nuclei, okay, that will remain after 80 hours is equals to 1 over 2 raised to power 4. So 1 raised to power 4 still remains 1, and 2 raised to power 4 is equals to 16. That is 2 times 2 times 2, which is 8, then times 2, which is 16. Okay, so n all over n naught is equals to 1 over 16, which represents the proportion of the original radioactive nuclei that will remain after 80 hours. Okay, and let's return back to the screen to continue with our lesson. So this is where we draw the curtain for the preview of today's video lesson. You can watch the complete video by simply clicking on the link in the description below, and that will take you to my school website. There you will have to subscribe to enjoy the complete video. So in the complete video, we talked about transmutation, we talked about the application of radioactivity, we talked about nuclear reaction, we even saw calculation on binding energy, and many more. So I believe you enjoyed the preview of the video which you've just watched. If yes, please do not forget to hit the like button, click on the subscribe button, and lastly, tap on the notification bell to get informed as soon as we release the next video.